My name is Mihal Brumbuli, and I'm an engineer at PragmaDev. And today I want to present to you our new deployment simulator of interconnected object following the ideas of the Internet of Things. So our new deployment simulator is based on a success story of a research project at the Humboldt University of Berlin, and which concerned the development of a decentralized earthquake early warning system. Usually earthquake early warning systems are centralized systems, and the idea was to utilize the concepts of Internet of Things and distribute the computation and also the ability to generate alarming messages in case of disasters and other scenarios that are life-threatening. So in this project, ad hoc hardware was developed, combined also with certain services, including operating system, middlewares, and one of the main applications that was actually very important was to develop an alarming protocol application that was intended to run on such a distributed infrastructure. And its goal was to generate in a distributed fashion an alarming messages so that it was intended to be distributed on all the nodes in a certain scenario. The technologies used for developing such kind of application were mainly standardized modeling languages like the specification and description language, and also other standardized languages of the ITUT like TTCN3 for testing and so on. But we were faced with one very important problem that had to do with the actual deployment, not only in the real sense of deploying such application, but also was very important to be able to analyze such kind of distributed application in order to be able to arrive at certain results prior to any deployment. So the project concluded actually in a successful deployment in Turkey, Istanbul, also in the Adlershof area of Berlin in Germany at the Humboldt University. And as I mentioned before, as a very important criteria was to be able to simulate such distributed infrastructure of interconnected objects with such kind of applications. At PragmaDev, we utilize such success story in the development and of our deployment simulator. The basic idea is that utilizing the specification and description language, and mainly a standardized language, you can define the architecture, the behavior of certain applications, which you can further simulate, but in a very small scenarios using the SDL built-in simulator. And the idea was to extend this concept and be able to generate a deployment model out of it so that you can simulate the actual deployment of such specifications. So to do so, we define components and distributable parts of the system, and nodes which act as interfaces to the network simulation models, so everything is transparent to the modeler, and we use the NS3 network simulation libraries to provide the underlying network models. We also use pair of identifiers to actually identify uniquely each of the components in the model. And also very important, be able to describe external messages that may be important in case of the scenario that I just mentioned. It has to do with the modeling of certain earthquake waves that act as an input to the actual, to the whole system and also to the application itself. So starting from a model, we can automatically generate a simulation executable And then afterwards, we can actually visualize the behavior of such application in a distributed environment. These include live or post-mortem visualization of the whole nodes, of the states of the application, packets exchanged between the nodes, and also at a more detailed level, the processes, the messages, the timers that timer-related events that are happening inside of the nodes, and we do so also utilizing standard message sequence charts. So I would like to present a very short demo of our approach. So for that I will use a very simple system, basically a client and a server, generic, just to illustrate the concepts. The basic idea is that external messages come from the environment which trigger a certain behavior to the client, for instance, and configure the whole system to run for a certain amount of messages exchanged. So the blocks client and server are actually composed of only one process, and the actual behaviors using SDL can be expressed using final state machine, involving timers, processes, and messages. So, as a first step, as I mentioned before, it is possible to simulate such model, of course, in a condensed scenario using one instance of a client and one instance of the server. And the whole sequence of events is visualized using message sequence charts. So if I stop for a moment the system and try to send a starting message just to trigger the behavior of the client in the beginning. So I would like to send this message to the client and then run the whole system. We can see here the whole behavior of the system. And if I continue just to trigger everything automatically so that I can arrive at the end. So the idea is that such kind of simulation can only handle a limited number of instances. Basically, our system architecture composed of one system instance of a client and a server in this case. So the idea of our deployment simulator is to actually be able to simulate such behavior in a distributed infrastructure, for example, composed of 100 nodes or even 1,000 nodes. So in this case, I will use a simple scenario trying to deploy the server in one node and also trying to create 99 instances of the server application in the remaining nodes. So the idea is that we utilize deployment diagrams to do so. So every of the components represent a deployment piece of our architecture, and the nodes provide a seamless interfacing to the underlying network protocols provided by the simulator. And in this case, TCP ports and IP addresses are used to uniquely identify each of these instances of the application in the distributed infrastructure. And also, an external file in tabular format can be used to describe the external messages with their names and parameters. These are messages that are coming from the environment, and in this case, these are messages that actually configure the behavior of the application. So, to to switch to the interesting part. So now I can run, or better simulate such scenario. So the tooling will automatically generate an executable simulation model out of the deployment diagrams and the specification of the architecture and behavior using the specification and description language. And after generating such executable, it will launch it automatically. And then visualize it in live mode. So every kind of event will be visualized in almost real time based on the generation of the events from the simulation. And in this view you can see the whole nodes, with this one being the actual server node and the other ones clients, with all the possible states and also the messages that are exchanged between those. So if I want further details on the behavior of the application, I can launch instances of message sequence chart tracer in order to visualize the actual internals of each of the nodes. So in principle, if during execution, if something is identified as a certain problem during execution or the behavior of the application in a distributed environment by means of visualizing the colors of the states or certain messages, then the problem can be identified in a distributed fashion, and then afterwards it is possible to go into each of the nodes to have the actual details of that execution. These traces can be further saved and then compared automatically into predefined scenarios that actually describes the desired behavior of the application. So after the live simulation is done, it is possible also to continue and step through the whole simulation in an event-based fashion or time-based fashion. So it is possible to step through the whole events that were generated by the simulation. So I can reset and then continue or step through the whole application again. And it's also possible, of course, to go into the details of the execution of each of the nodes and have message sequence charts visualized for each of them. So, thank you very much. This is the presentation. Thank you.
Thanks to you.